Welcome. Today I want to talk about the quantum Fourier transform. It's a very foundational algorithm in quantum computing, in the sense that a lot of other algorithms rely on it as one of the steps in those algorithms. Shor's algorithm, for example, relies on the quantum Fourier transform in one step. Shor's algorithm is used to factor numbers for something like an RSA encryption. It's also used to calculate discrete logarithms. There's also the quantum algorithm to compute the eigenvalues of unitary matrices. This relies on the quantum Fourier transform at one point. There are a bunch of other algorithms that all kind of rely on this, and generally there are a lot of algorithms that rely on the discrete Fourier transform. So this is an extremely important uh, algorithm, and its discovery led to quickly a lot of other algorithms kind of springing up in its wake. So let's talk about what a Fourier transform is first off. We're going to be discussing the discrete Fourier transform, which is a mapping between space and generally some other variable, but for now we'll just say frequency. Good way to think about this, say we have f of x, and we're plotting it and imagining it over x, and it's expressed as a function over x. Now let's switch to frequency space. Maybe it looks something like this. That is, this particular frequency has a high amplitude, this particular frequency has a lower amplitude, and each one of these frequencies, when added together, will actually make this. You can think about this in terms of music theory. A chord is made up of different notes. In the same way, this function up here is made up of many different frequencies. Some have larger amplitudes, some have lower amplitudes, but if you add them all together, then they will actually give you f of x. And in particular, that's the formula for the Fourier transformation. It's a sum over these frequencies of the frequencies themselves. This is a sinusoidal. Frequency times x over n times this amplitude, this weighting of each frequency mode. Summed together will give you f of x. This is the discrete Fourier transformation. Computationally speaking, it requires n squared operations where n is the size of the input. You have an input bit, and it's like 1, 0, 0, 1, 0, something like that, n equals 4 then. So the order, the asymptotic order, we can review this really quick, but if you have something like n squared plus n plus 5, you take n to infinity, and at infinity, this is so significantly larger than this and this that you can kind of forget about that, and asymptotically, it approaches n squared. That's what this big O notation means. So this is the number of operations required to compute the discrete Fourier transformation. And you can sort of see this because to get let's transform frequencies to space. It's a matrix acting on a vector, and each one of these little things here has an x and an omega. So for each x and each omega, you need to compute one of these terms. And there are n x's and there are n omegas. So n squared. There are n squared of these terms. Let's speed up a bit. We can actually speed it up a bit within the realm of classical computation with what's known as a fast Fourier transform. In a fast Fourier transform, the first step is switching to base 2, also known as binary. When you express an integer ordinarily, or any kind of number at all, tacitly you're saying it's in base 10 because it's expanded in powers of 10. 10 to the 0 equals 1, 10 to the 2 or 10 to the 1 equals 10 times 2 plus this times 5. 3 times 10 to the 2 is 100. So far we have 325. It's in powers of 2. This is in powers of 2. Or this is in powers of 10, rather. This is in powers of 2. So this is 2 to the 0. This is 2 to the 1. This is 2 to the 2. This is 2 to the 3 equals 8. So that's binary. So we're going to switch to base 2. So x will look like this. All the way to x of 0 times 2 to the 0 equals 1. And y will also look this way. So in this Fourier transform, notice that we have this term in the exponent. And right, so I'm using y here instead of frequency. Normally a Fourier transform goes between space and frequency space. In general, it doesn't have to be that way. You can transform between arbitrary basis and a generalization. In particular, since we're talking about quantum mechanics, our ordinary wave function is an eigenstate of energy and an eigenstate of position, or an eigenstate of position rather, not energy. You need to make superpositions to get eigenstates of energy. And in order to know where the particle is, if we square this, we get the probability of where the particle is in space. You can actually do a Fourier transform on this in order to get the momentum wave function. That's why I was using k before. So if you square this, it will give you the probability that your particle has a given momentum. So it doesn't have to be to frequency. It could be between space and momentum. In general, it will be between x and y, two different bases. So that's why I'm using y here. Okay, back to this. Notice this term. And n equals 2 to the power of n, because that's the dimension of our space. If you have n bits, there are 2 to the n combinations. And if you have n qubits, the dimension of the space is 2 to the n. So that's what we're summing over. All right, so this term here will look like this. And I'll explain what this is in a bit. So all the way out to y0 times this whole thing. X of 0. And what's this? This is the binary expansion of x divided by 2 over n. So it's going to look like this. Let's say n equals 3. Then we're going to have x3 plus x2 plus x1, where this is the biggest digit in the binary. It would be 4, 2 to the power of 2. And this is the smallest digit in binary. So this is going to be over 2. This is going to be over 2 to the 2, or 2 to the 1. And this will be over 2 to the 2. So if we're talking about x3, x2, and x1, that's what this will look like here. So that's this expansion up here. Now let's kind of plug this in. Remember, we're summing over y now instead of frequency because it can be any basis. So f to the y. Let's plug this into here. And what we're going to get is this. et cetera, right? We all know that right? So what this is actually going to be is a number of factors. XO times e to the I pi m minus 2 x1 xo, et cetera, et cetera, et cetera. There'll be n of these. N of these terms. And each term is a sum that can be done in constant time. There are n of them, so these sums can all be done sequentially in linear time in n. So these have to be done one at a time, and then they can be multiplied together for a total number of operations of n log n. That's the fast Fourier transform. We can do even better with quantum because of parallelism. So originally up there, we had all those kinds of terms and these y digits here, the y digits. So classically, you need to probe every single y digit one at a time. They're binary digits, they're mod 2, so they can either be 0 or 1. With quantum parallelism, in quantum computing with this algorithm, we can actually simultaneously probe the value of 0 and 1 at the same time because we can use quantum superpositions. So we actually get something like this in quantum. Actually, can make that implicit. E to the power of 2 pi I x y over n. This is y. Y is 0, so it's just xo, right? Plus. So since this is 0, this just goes to 1 plus 1 plus e to the power of 2 pi I xo times, now we can set it to 1 because y can only be 0 or 1. It's a binary digit. Times 1. So it's just whatever xo is. Times the same thing. 2 pi I. Again, we've set y equal to 1, so it's just times 1. All right, so it's just terms like this. That's what we're going to get in the end of the quantum Fourier transform. Now, what's interesting about these is that these qubits aren't entangled, actually. When you've seen quantum states before, you might have seen something like this. So if you measure this bit, you know where this qubit is. Sorry, if you measure this qubit, you know where this qubit is. These are not entangled with each other. They're actually independent. So that takes the dimension of the Hilbert space from 2n down to n. So we should really expect an efficient algorithm here. And in fact, there is one. Let's say these are the binary digits of our first basis x. Oh, x0. The circuit, it goes like this. Let's see if I can remember it. R2 output. And these are the digits of the new basis after the Fourier transform. Let me double check to make sure that's correct. Oh, I forgot an R1 here. All right. All right, let's run through this circuit with an example. Let's say X is that, these three digits. So the first is 0. X1 equals 1. X0 equals 0 again. So after hitting the Hadamard gate, 0 turns into, this is a cat. So hitting the Hadamard gate, 0 turns into 0 plus 1, this superposition. We remember Hadamard gates. I'll go over them real quick just in case. Takes a 0 to this superposition. 0 plus 1. And it takes a 1 to this superposition. Hold on. And it takes a 0. Very good. It takes a 0 to this superposition. What about R? R is actually a controlled gate. So only if this little dot down here, only if this little dot gets a 1 does it do anything. Otherwise, it just acts trivially. If it's a 0, it doesn't do anything. It just acts trivially. It's a controlled gate. It's a generalization of the controlled knot. It's a controlled phase shift gate. Essentially, if you get 1, 1, if both input bits are 1, then and only then will it add a phase onto it. Like so. Where D is the distance between the qubits. Okay, now we can run through the circuit. All right, so we get this Hadamard gate, and then this is a 1, so this does in fact act on the Hadamard gate, or on the result of the output of the Hadamard gate, and it basically sticks this phase onto it. Phase, and it's over 2 to the D. The distance is 1 because these are 1 away. So it's just over 2, and that's multiplied by the original square root of 2, and then you get the same state there. It's just adding a phase, an overall phase to it. R2 doesn't fire because this is a 0 here. So this kind of just gets passed on to the end, and this is your Y0. Let's do this one. All right, so 1 goes through the Hadamard gate, and a Hadamard gate turns a 1 into this superposition. And again, this is a 0, so this R1 doesn't fire. So this gets just passed on to the end. No phase. It's just, this is Y1. And now 0 goes through this Hadamard gate. And this is Y2. Okay, so this is our new state. This is our new basis. It's an example of the quantum Fourier transform doing its thing. Okay, so this is nice. In terms of gate size, the number of total gates in the circuit, classically, the number of gates we would need to do a discrete Fourier transform is exponential. Quantum, 10 squared. That's very nice. This is a number of gates. In terms of number of operations, classically, it's O to the n squared. And quantum, it's log n squared. That's a very nice reduction. Good. So This is actually an example of a hard problem classically being reduced to polynomial gate size with the quantum algorithm. So great. So quantum Fourier transform. Um, that's basically in a nutshell. There's your example of it running through the circuit. And if you guys have any questions on the quantum Fourier transform or anything at all, feel free to leave a comment or drop a DM or anything like that. So thanks for listening as always. Hope you guys enjoyed, and I'll see you next.